Today I want to talk about some basic vector math because I'm going to be making videos on things like raycasting. I've already made some videos that used a bit of vector math, so I'm going to explain some very basic vector operations. So here's some topics that I'm going to look at, and I'm going to start by describing a vector direction, and what I'm going to do is talk about it in one dimension. And I don't really know if there's such a thing as one-dimensional vector. I don't think that there technically is, but just for the purposes of this description, I think it kind of makes sense. So I'm going to make a new vector. I'm going to call it 1. And this is a direction vector because it has a length of 1. It starts at the origin on a flat number line and moves to the point 1, so it has a direction to the right and a length of 1. And there's one other direction vector in one direction, and that's the vector -1. And it starts at the origin and moves to -1. So let's take a vector like 5 and figure out its length. So to find the magnitude of the vector 5, we take the square root of the sum of each component squared. There's only one component, so the square root of 5 squared is equal to 5. And then to extract a direction vector from this, I'll divide each component by the total magnitude. So there's only one component, that's 5, divided by the total magnitude. It's equal to the direction vector 1. So the direction vector 5 is equal to 5 times the direction vector 1. And in linear algebra, this is called a scalar because it scales the length of a vector. And this vector, you could call it direction v, and you draw a hat symbol to differentiate it from normal variables. That's equal to 1, and you could call this any variable you wanted. You could call it a, or you could call it the magnitude, and you can write a direction of v is equal to v, or v magnitude times the direction of v is equal to v. A lot of different ways to write it. So I'll do one more vector, do -3, and extract the magnitude. So the square root of -3 squared is +3. And to get the direction, divide each component by the total magnitude, and you get the direction vector -1. So the vector -3, is equal to 3 times the direction vector -1. So move to 2 dimensions. And here's my XY axis. And in algebra, you just call them points. So take the point 6, 6. You can also call this a vector by drawing an arrow that starts at the origin and points to 6, 6. And that's the vector v equals 6, 6. To find the magnitude, you take the square root of the sum of each component squared. So 6 squared plus 6 squared is equal to 6 root 2. So the length of this line that runs from the origin to the point 6, 6 is about 8.5. Now to extract the direction, divide each component by the total magnitude. And the 6's cancel, so you get 1 over root 2. And 1 over root 2 is usually written as root 2 over 2. So I had another vector that was in the same direction, say it points to 1, 1. Then I have the vector 1, 1. And it has the same direction. So it's equal to some magnitude times the direction vector 1 over root 2, 1 over root 2. And to find the magnitude, use the Pythagorean theorem. A squared plus b squared equals c squared. And then solve for c. Take the square of both sides, square root. And you get root 2. So 1, 1 is equal to root 2 times the direction vector 1 over root 2, 1 over root 2, and 6, 6 is 6 root 2, 1 over root 2, 1 over root 2. And to get back the original vectors from magnitude and direction, you just multiply the magnitude times each component. The root 2's will cancel and you'll get 1, 1. Same here, the root 2's will cancel and you'll get 6, 6. So this direction vector, root 2 over 2, if you draw in a unit circle, has a radius of 1. The point of intersection makes a direction vector, and this direction vector has a length of 1. It's equal to root 2 over 2, comma root 2 over 2. So that. And another way to find this is if we knew that the angle was 45 degrees, then to extract the x value of this point, take the cosine of 45 degrees, and you get root 2 over 2. And to extract the y, you use sine. Do the same thing. So because these two vectors lie along the same line, They have some relationships that are the same as would be on the normal flat number line. So if we rotate both these vectors down flat, then this vector 1, 1 comes to its magnitude, root 2, and 6, 6 comes to its magnitude, 6 root 2, which is about 8.5. So if we add their magnitudes, root 2 plus 6 root 2, you get 7 root 2. Another way to add these is as vectors. 1, 1 plus 6, 6. And the way to add vectors is component-wise. You add the x's, and then you add the y's. So you get 7, 7. And the magnitude of 7, 7 is equal to 7 root 2, which is equal to that. So the way these vectors add as vectors and as numbers is the same. And you could think of vectors as being magnitude that live on a different number line. And in this case, it's the number line root 2 over 2, root 2 over 2. But for any vectors that live on the same direction, and there are an infinite number of directions, you have a direction that goes this way, a direction that goes this way. And for any vectors that live on the same direction, the same rules of algebra will apply. So because magnitude is a really fundamental concept, I'm going to load this script that makes an object that forms the hypotenuse of a right triangle in a square. So I'll show what this looks like. So I'm making 2 random legs, solving for C, then I'm positioning C into so that it forms C squared. So I'm going to call A the shorter side, B the longer side, and here's the hypotenuse. You can shows up 4 times. There are 4 rectangles, one here, 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 here. Each one is equal to AB. So each one of these smaller is just the formula for area of a triangle that you learned in algebra class. So each of these is AB over 2. This length is B minus A. This whole width is A plus B. So looking at this image, there are a few relationships that just kind of pop out. One of them is a plus b squared equals 4ab plus b minus a squared. It's that part in the middle, and each one of these is an ab. You can combine them in a few more ways. You could use c squared, and then what's left is 2ab. You could kind of rotate this, and here you have b squared. Here's a squared. Here's an ab. Here's an ab. So that's kind of the normal way you would expand this if you were using FOIL. So a plus b squared is equal to b squared plus 2ab plus a squared. There's a relationship you can't really see. B squared, c squared plus a, c minus a. And those are conjugates. And they're pretty interesting, and they show up in a lot of places, and it's good to know why they show up and what they mean. If I divide this up a little more, I draw a line from here to there. That shows up in 4 places. There, there, and there. This edge is b minus a, this edge is a. So each one of these triangles is a times b minus a over 2. So if you add all those up, you can see c squared is equal to 4. There's 4 of them. Plus this piece in the middle, b minus a squared plus these pieces, which I'll call x. So I'll just write 4x. And if I did that right, and if you solve for x, then you'll get x equals a squared over 2. And so if you pick any 2, then the region within c squared is equal to b squared, since a squared plus b squared equals c squared. So I just wanted to show that because some things you can just see. You don't even have to manipulate these symbols or move them around too much. They just kind of jump out at you. The next thing I'm going to talk about is vector origins. So I mentioned that on an axis, a vector starts at the origin and moves towards a point, but it can be translated. So say I have 1, 1, and I have 2, 1, and I add those together. And that's like putting the tail of this and placing it at the head there. And that can be thought of as a new vector. That is equal to 3, 2. Plus 2, 1. And with any two vectors, not counting this one, you can use subtraction to get the last vector. And when you subtract vectors, you get a vector that points from the second to the first, and that's equivalent to a number line, where if you called one vector, say 3, and another vector 2, and you wanted a vector, say, that points from 3 to 2, let's call this A, call this B. So to get a vector that points from B to A, you subtract A minus B. To get a vector that points from A to B, you subtract B minus A. So let's take a cube and move it to some random position. If I select one of these vertices, it gives a local position, -1, -1, 1, and Z. And that can be thought of as a vector that points from the object's origin to the vertex. And if I wanted to figure out the global position from the origin, then I would add the location of the object. That's this vector. So global position plus the local vector is equal to the world position of the vertex. And if any two of those were known and you wanted to find the last one, you could subtract. So if you knew the world position of the vertex and the local position of the vertex, then you could subtract to get the world position of the object. And one thing that vectors are really useful for is for describing a velocity. So let's say I have an object and it's moving 2 meters per second to the right. So my magnitude is 2 and my direction is 1, 0. After 1 second, the position of the object will be at the head of the vector, and then you could update the vector to be relative to the object itself. And that's a different way to think of vector origins, even though they're thought of as originating at the center. All vectors don't have to have the same center. They can be defined in terms of a relative center. Either way, in the case of a velocity, the math turns out to be the same. But this is kind of helpful for thinking about it this way, because it's almost like the vector is a force, which is appropriate because velocity is caused by force. But it's almost as if this vector is kind of pulling this object along. So what about gravity? Gravity is an acceleration, so does it make any sense to draw a vector that starts at the object and say points down to represent the downward acceleration? And it kind of makes sense, but it makes a better sense to describe the acceleration acting on the velocity of the object rather than the object itself. So let's look at this object at time 0. And if I have an object falling under gravity, then the position of the object is described by this equation, and that's if the original velocity is 0, and if the original position is 0, I'll put it at y equals 0. So just to keep it simple, I'm going to say that a equals -1, and actually it's -9.8 meters per second squared, but it'll be easier to set it to -1 meters per second squared. So if I solve this for time 1, then I'll get 1/2. So my object is here. This is falling under gravity after 1 second. After 2 seconds, we've got 2 squared is 4, divided by 2 is 2. After 3 seconds, 3 squared is 9, divided by 2 is 4.5. So 1, 2, 3, 4.5. So the velocity, the equation for the velocity of this object is the derivative of the position. So the derivative of this function is equal to velocity, which is at. So at point 0, here velocity is 0, time is 0, acceleration is -1. At 1 second, velocity is -1. So I'm going to draw a vector that has the length of 1. After 2 seconds, velocity is 2. So draw a vector with length 2. After 3 seconds, it's 3. 1, 2, 3. So now what I'm going to do is redraw this, but I'm going to fix the position of the ball and redraw the vectors. So here's time 0, time 1, time 2, and time 3. I'll redraw my velocity vectors. I messed that up, sorry. So now I'll draw the acceleration. And that's just a constant. It's always equal to -1. So with respect to velocity and acceleration, the magnitude of the velocity vector acts kind of like the position of the ball over here, where each second the velocity takes the place of the acceleration, and that works because acceleration is constant. And here it doesn't work because this velocity vector is constantly changing, so you can't simply add the vector to the position of the ball, because you have to account for all this continuous change in velocity between each second. So I have a script of this bouncing ball that I can show. And it's just a ball or an object or whatever falling under gravity. And I've got a vector, an XYZ vector, and I can set this manually, and that ball will continue in that direction forever because there's nothing to change it. Z doesn't work quite like that because it has gravity constantly working on it, so it's not changing linearly. So I'll show what this gravity script looks like. It's pretty simple. The collision is fixed. It's not based on collision with a real object. It just checks if the ball falls under 0. I'm reading my velocity. I'm setting my bounce, which is the elasticity of the object. Acceleration due to gravity should be 9.8. Here I'm drawing my velocity vector relative to the position of the ball. I'm drawing an acceleration vector relative to the position of the velocity. To add the x and y velocity, you just add it to the position, similar to like where I showed the ball moving at 2 meters per second. Each frame in my game is running at 60 frames per second. So each frame I increment by an acceleration multiplied by delta time. Delta time is 1/60. I get this delta position, which is kind of like an accumulation function, and then I update the position of the ball. Here I check if it fell below 0, and then I get a new height determined by the bounce variable, and then I restore that height. So my object starts at 10, and I multiply it by 0.8, so after the first bounce it's going to move back up to 8. Then I store it so that it can be reduced again. I reflect the object across the ground plane. My ball is moving in increments, and at some point it's going to pass through the ground. So I have to put that position back. So I reflect it here. And then if my new height is 8, say 8 is somewhere up here, then I'm going to find the time it takes for the ball to fall from that height to there, and that will give me the velocity I need to get the ball back up. So here's where I solve for time based on the new height, and then I get a new velocity, and I set velocity to the opposite of v to send it back up. This is an outdated script I need to reload, but this is what I was going to do next, is freeze the position of the ball. Well, actually, not that. First, I'm going to step the ball. So I'll try reloading this. So now it's not moving. Still not updating, I'm not sure what's going on. Okay. So now I can step through one frame at a time, and you can barely see, or maybe you can see this velocity vector growing as the object falls. I can zoom in on that to show it a little better. And it's too small to see, but somewhere in there there's a acceleration vector. And so now what I want to do is freeze the position of my ball, and that way I can watch the vector grow. And to make the vector more visible, I can up the acceleration. So now you can see this gravity vector, and after each frame the head of the velocity takes the place of the head of the acceleration vector, and then the acceleration vector gets updated. So I think that's all I wanted to show with that. So the reason this velocity gets reflected upwards is because if I have a ground plane, I have a normal that points up, so my ball is moving down, and the orientation of this plane reflects it directly back up. If I make like a plane, you can see the normals here. So normal of a plane extends, it's a vector basically that has the length of 1, and it extends orthogonal or perpendicular to this plane. So you could update this to find a collision with a certain object, and say this plane was like this, and the ball collides and then it's going to reflect in the direction of based on the normal of this plane. And one of the things you'd use to calculate that is the dot product. That's what I'm going to talk about next. So I think of the dot product as fundamentally being vector multiplication. And to show that, let's go back to this 1, 1 and this 6, 6 vector. The dot product is essentially an algorithm, and it's equal to u1 times v1 plus u2 times v2, and you continue for as many dimensions as are in the vector. The vectors have to have the same dimensions to dot them. So if I wanted to dot 1, 1 and 6, 6, then I get 6 times 1, comma, or I'm sorry, this is not a vector, I shouldn't have drawn brackets. This is 6 times 1 plus 6 times 1 equals 12. So remember that the magnitude here is square root of 2. Magnitude here is 6 square root of 2. And if I multiply those magnitudes, 2 root 2 times I need to section these. Whoops, sorry, this is 6 root 2, there we go. Okay, so I don't need parentheses. But that basically goes back to what I was saying about these two vectors living on the same direction that have the same algebraic properties as vectors that live on the number line, which you would call ordinary numbers, basically. So another way to think of these vectors is they're just numbers, but they live in a different direction as numbers in normal algebra. So when you're writing 1, 1 as this, then you could think of this as fundamentally being the vector or the value, and you could think of this as almost being like a space, like a different kind of space. And what this also kind of shows is that the dot product is analogous to multiplication in regular algebra. So let's take the vector 1, 2, 3, and I'm going to dot it with itself. So v dot v is equal to 1 times 1 plus 2 times 2 plus 3 times 3 and that's equal to 14. And notice that we're halfway to getting the magnitude of the vector. The only thing we have to do is take the root of this. So the magnitude of v is equal to the root of v dotted with itself. Another way to write the dot product is like this. It's equal to cosine of theta times the magnitude of u times the magnitude of v. And theta is equal to the angle between u and v. So let's go ahead and show that because this is pretty important. I'm going to open up a new script, and I'm going to get two new random vectors. So I'm going to import random, and I'll seed random, x equals random dot random. And do it again to get a y. And then I'll make a new vector u. And then I'll get a vector v. And then I'll dot these. Dot equals u0 times v0 plus, I keep adding brackets to this stuff. There's no brackets around dot product. It's just a normal decimal variable. u1 times uv, oops, times v1 So there's the dot product, if I did that right. So let's do it this other way. So first I'll find the mag of u and the mag of v. And I'll just use the maths hypotenuse function for that. And that works for vectors in 2 dimensions. So you just pass an x and a y, and you'll get back the total magnitude. Do the same thing to get the v. And that's pretty straightforward. To find the angle between the vectors, I'll use arc sine. So if you have a vector, say I have v here, u here, v theta is equal to inverse tangent of vy over vx. U theta is the same. And then theta, the angle between the vectors, is equal to v theta minus u theta. So I'll do that. angle of u is equal to math dot a tan 2, and you put y first, then you put x, angle v is the same. Then I'll get theta, angle v minus angle u. And then I'll show that cosine of theta times the mag of u times the mag of v, print dot. So these two prints should be the same. So one thing that you can arrive at with this formula is you could solve for theta, and if vectors u and v are known, I'll divide these, bring them over here, so you get u dot v over mag of u times mag of v is equal to cosine theta. Then take the inverse cosine of both sides, and you get theta is equal to u dot v over mag of u times mag of v. And this is pretty nice because these vectors can have any dimension, and you can find their angle that way. So I'm going to look more at this. This might have a name, but I don't know what it's called. You could call it the cosine of theta, or maybe call it C. I could call it the common normal magnitude, or the common directional magnitude, or you could call it the normal parallel component. There are a lot of different ways to think of it, but basically it's I call it the common normal magnitude because you're dividing these magnitudes out. So say you have a vector that's flush with the x-axis, and let's go back to this vector root 2 over 2. This cosine theta value will just be equal to this x, because that's what cosine does. It extracts the x from the unit circle. And here's theta. This is the angle between two vectors. And I could rotate both of these vectors, and it's not going to change. Say I have one vector like this, and I've rotated these 45 degrees. So my theta is the same. And if I find the intersection from, if I move in a point or in a line parallel to one vector and meet the end of the other vector, this length is cosine of theta, or you could call it the common normal magnitude. You could describe it a lot of different ways. You can also go parallel to here and intersect with the end of that vector, and you get this length, which is the same. Those two will be equivalent. So one way to think of this dot product is, this isn't the best way to think of it, but it can be useful for predicting what a value of a dot product should be. So say I take, or let me just draw two new vectors. It doesn't matter what they are, but let's just say one vector has a magnitude of 5 and another has a magnitude of 4. You multiply those together, you get 20. Then you find the cosine of the theta, and you would get something like, I have no idea, but let's just say it's 0.5. So you'd expect the dot product of these two vectors to come to 10. So one way to think of this is to take these two vectors and form an area, form a rectangle, and that rectangle has an area of 20. And then you kind of scale down this area by a factor. This value, cosine of theta, wherever I put it, here, is going to be between -1 and 1. So you could think of that as kind of, this area represents a kind of maximum. It's a kind of upper limit if the vectors are perfectly aligned. But if they're less than perfectly aligned, then this portion of the dot product starts to move towards 0. And so it's kind of like you're scaling this down. If you keep the magnitudes the same, but you rotate one vector towards the other vector, then you're kind of scaling down this total magnitude. And you probably don't want to think of vectors as area, but it's kind of useful for making a kind of mental image to predict the result of the dot product. So say I have a vector that's even with the x-axis, and I have another vector that points straight up. Another way to think about this cosine of theta value is, well, let's first say I have two vectors that are directly aligned, then cosine of theta is 1. If I have one vector here and one vector that looks like this, and they're perfectly perpendicular. Another way to think of this is any vector moving up in y, if you look at it in terms of the width of this vector, it will never have any width. It will always be 0. I mean, you can also think of it as angle, because the cosine of 0 is 1, and the cosine of 90 is 0, and the cosine of 180 is -1. So if I have one vector here and one vector here, then cosine of theta is -1. If I have one vector here and one vector here, cosine of theta is 0. And any value in between these will fill in the values between 1 and 0. This fills in the values between 0 and 1. So you can rotate you can rotate your vectors relative to each other. So if I rotate this, then it's the relative change that's important. It's the angle between the vectors. So a vectors like this, they're still perpendicular, so their dot product, well, their cosine of theta will still be 0, and therefore the entire dot product will also be 0. So I'll show an application of the dot product. Say I was making a game and I have an enemy and he's facing this way, and I have a player and he's here. I can use the dot product to determine whether my player is within the peripheral vision of the enemy, assuming my peripheral vision is 180. It's basically a facing function, and if you have a plane and I rotate it in any direction, and I take another point, a sphere, and I draw a vector from the center, or it could be any point on the plane actually, but usually it's convenient to use the center because that's how polygons are stored. So you draw a vector from the center to the point, and then you dot it with the normal of the plane, and if the dot is less than 0, then the point is behind the plane. If it's greater than 0, then the point is in front of the plane, or if it's equal to 0, the point is on the plane. So going back to this, if I draw a vector from my enemy to my player and then dot the facing direction of the enemy, then in this case my dot will be less than 0. So something that might break this is if I have like an obstacle, like a wall, and my player is here, then the dot product will be positive, and the game will register that the enemy can see the player. And one way to fix that is with a raycast, where you can look for an intersection between the obstacle and the line of sight. Or you can use trigonometry if you're using it in 2 dimensions, but the dot product will work in 3 dimensions. Another way to fix this without using a raycast is if I had a ground and I split this ground into 2 different pieces along the wall, and I checked which ground the player is standing on, then I'll have 2 checks. I'll have this ground and dot greater than 0. So I'll show how that works. Copy my gravity script, and I'll call this facing. And I'll just get rid of all of this. And the first thing I want to do is get my normal, so I'm just going to hard code it. So I'm going to apply the rotation and look it up in the console. And then I need my center. In this case, the center of the plane is equal to the location of the plane, so I'll just use the location. Then I need to get the position of my point, which might be like my player. And then I need to make a vector that points from the center of the plane to the point. So and then I just have to dot that with a normal. So dot equals and then I'll store that. And I'll debug this. Okay, so there's my dot. So I'll add some controls. I'll place my camera. So you can see the dot change in real time, and as soon as it moves behind the plane, as soon as it disappears, that's when it becomes negative. So I think the next thing I'm going to talk about is vector projection. So if you have two vectors, and let's say I want to project this vector onto this vector, I'm basically saying that there's a right angle that exists along this direction that meets the endpoint of this vector, and the projection will form a new vector, and it has the direction of the vector being projected onto, but it's in terms of a different magnitude, and the magnitude is partly determined by the angle between the vectors. One way people describe this is if you have like a light and you're shining it down in perpendicular to the vector being projected onto, then the new vector is kind of like a shadow. And the thing that used to confuse me at first about that is you have to extend this vector into infinity. So you have to have extra space for a shadow to land. So there's another way to think of a projection. I have a blend file to show that. So here are two vectors, and you can think of them as sort of like piping. And here I have a sort of like T-joint, and into this T-joint I have another pipe fixed. So say I want to project this vector onto here. I'm going to copy this angle, and then I'm just going to slide this until it hits the tip of this other vector. So the result is this. If I wanted to do the opposite, project this vector onto here, then I'll copy this angle, and I'll flip this, and then I'll move this, and even though I'm off of this vector, I still keep moving until I reach the end. Like I said, you have to extend this vector into infinity, and that makes a new vector that looks like this. So basically, for the vector being projected onto, only the direction matters. It has nothing to do with the magnitude of this vector being projected onto. And that might be a little bit confusing when you see the formula. The projection of V onto U is equal to U dot V over U dot U times U. This is a scalar, and this is a vector. So it sort of looks like the magnitude would come into play because this formula is written in terms of the vector being projected onto, But here in the denominator, you're actually dividing out the magnitude of that vector. So remember, the root of u dot u is equal to the magnitude of u. One way to make this maybe a little less confusing is to rewrite this formula. So instead of using u, I'll use the direction of u. So I'll make a vector called w, and it's equal to u over the mag of u. And then I'll solve for u and bring this over here. U is equal to w times the mag of u. And then I'll put this u into here, or I'll put this side in there. So you have u dot v over v dot v times w, and up here you stick the mag of u. And then the next thing I'm going to do is rewrite this in terms of the common normal magnitude, or the cosine of theta, which is equal to u dot v over mag of u times mag of v. So this is already taken care of, this u dot v, so I could cancel that. There's no u dot v, or I'm sorry, there's no mag of u times mag of v. So to balance that out, I need to stick these in the numerator. So put these in the numerator, mag of u times mag of v times mag of u over u dot u times c times w. So now I can simplify mag of u times mag of u is equal to u dot u, and that's because root of u dot u is equal to the mag of u. So I get u dot u u dot u times the mag of v over u dot u times c times the direction of u. U dot u over u dot u cancels. So the projection of v onto u is equal to the magnitude of v times the magnitude common to both times the direction of u. And here I've got a direction vector, and here I've got the length of the vector. So this length here would be, well, this is, well, it doesn't matter, but that's the magnitude of the new projected vector. So one application of vector projection is to find the shortest distance from a point to a plane. So here I have a plane. Here's a point. 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 Here's a point So if I have a point on this plane, and I have the normal, and I have this point, then I have everything I need to find a vector that points from this point directly to the plane, the smallest possible vector. So to do that, I'm going to draw a vector from this point to the center. And then I think I'm going to project that onto the normal of the plane, and that will give me this. And that works because the normal, the direction of the normal is always the shortest path to the plane. So let's try that. I'm going to get the normal of the plane and position of the plane again. I need to make sure I apply the rotation so that I get the normal as a world vector. The center is just equal to the location. Now I get the location of the sphere. Now I need to draw a vector from the point to the plane. Then I'll use the projection formula. So dot is equal to vec dot norm. And on my denominator, I'm projecting v onto n. So my denominator is norm dot norm. And actually that's equal to 1. So I don't need to divide anything. I just need to multiply this value, or I need to scale my vector up by this dot. So norm might mess this up. I mess it up a lot. I get a vector that's backwards or put something in the wrong place, so we'll see what happens. We'll draw this vector. And that's going to draw it at the origin. And I'll just move it to the point. So selection to cursor. Okay, so that worked. I drew a vector at the origin, and then I place that vector at the position of my point, and that vector just barely touches the point on the plane, and that's the shortest path. And I also have a function for that. There's my facing function that I showed earlier. There's a projection function. Here's the distance from a point to a plane, and that gives a magnitude. It doesn't actually give the vector, but then you can normalize and then rescale the normal vector and put it at the point to basically do the same thing. Next thing I'm going to do is this. So now is where you finally get to the meat of ray casting, and there's quite a bit of things involved in ray casting, especially to do it efficiently. The only thing I'm going to talk about is if I have a ray and it's some direction, say it's in the direction of this vector, and I have an infinite plane, how do I determine the intersection between the ray in this direction that starts at this point and the plane? So this is different from the previous problem, because before we were just finding a direct point. In this case, I might be pointing like a bow and arrow at like a target, and I want to know if I continue that arrow straight into space, where is it going to intersect with this plane? So to solve that, it's somewhat similar to what we just did. So let's write what we just did. We did a projection which was equal to this, and u in this case was the normal. So I'll rewrite this as nv over nn times n, and the vector was from the point to the plane. I'll call it C for center. So X is a point, C is the plane, or that's backwards, sorry. It's C minus X, so that points from the point to the plane, and that's what V is equal to. And then plug and chug the rest, and you'll get a vector that moves to the shortest point. So for this intersection problem, we're doing a similar thing, except we're going to use a different point, and the point we're going to use instead of using the center is, well, first of all, we are going to use the center, and we're going to do that same exact thing as we're going to find the shortest path to the plane, and then we're going to do another projection. And that projection is we're going to take the exact intersection, which is also a point on the plane, because before we used the center, and that center was a point on the plane. This time we're going to use the intersection, which we don't know what it is, but that's what we're going to solve for. So we have our projection formula, and that's the same. We're going to do a new projection from the ray we're going to project the ray onto the normal, and we're going to use the same vector, I think. So instead of V here, we're going to use our ray direction. Say that's the direction of our bow or whatever, and do the same thing, project it onto the normal. And so our formula is the same, and in both cases that's going to be equal to the shortest path to the plane. So that means that these are equal to each other. So set them equal to each other. It's equal to nr over nn times n. And solving linear algebra equations can be a little bit tricky sometimes because you can't just pull apart these dots. It's not the same as dividing them out. It doesn't quite work like that, I think. But one thing I think you can do is just cancel these vectors, because you're comparing, same to same. And these are both scalars, so you're comparing the same thing to the same thing. So I can get rid of these ends on the bottom. Anyways, they're equal to 1, so it wouldn't actually matter. And you get the normal dotted with the ray is equal to the normal dotted with the vector towards the plane. And so I'm going to dot these out, and I'm going to get the magnitude of the normal times the magnitude of the ray times the direction of the normal dotted with the direction of the ray, and that's equal to NV. Then the magnitude of the normal is 1, so we can just cross that out. So we get the distance. This is going to be the distance to the intersection. And then if I want to find the ray itself, then I can always go back and scale that ray according to this magnitude. So I'm going to divide this, and I get this. And these are both normalized vectors, so I think you need to normalize the ray before you use this formula. But you get the magnitude of the ray is equal to n dot v over nd dot rd. And let's see if I did that correctly, or if I got something backwards. So my denominator is equal to my ray direction dotted with my norm, and my numerator is my vector from the point to the plane dotted with the norm. So I think that is correct. So I'm getting pretty close to all I wanted to talk about. The last thing I'm not going to show how to do because it's very complicated and very time consuming, but if you wanted to make a 3D game engine, you have a bunch of planes in space, and you have to figure out which plane lies on top of different planes. You have to determine the order, and that's pretty difficult. But one problem using vectors that's actually pretty easy is to find the position of the vectors in 3D space relative to a camera. So to put 3D points onto a 2D plane like a camera, you could think of a camera similar to this, basically a big pyramid. So I'll make a pyramid, and I could think of this as my camera, except this basically extends infinitely. So I can drag this face out, scale it up, and this is my camera. And say I have an object like a plane that I want to know the points of. Oops, or I meant to do an object like a cube that I want to know the points of. And my cube is inside my viewing region here. If I have three vectors, like this green vector here, call this U, call this one V, and then another vector similar to this but that points inwards, call that W. For each of these vertices, all I have to do is draw a vector that starts from the origin of my camera to each point, and then what I want to do is get a plane that's parallel to this. So I could use this as an example. I want to get a plane. Say I'm finding this corner vertex. I want a plane that bisects this vertex along the direction of this W vector, and that will tell me the distance from my camera origin to this cube. So what I want to do is divide that distance out, and that will give the illusion of perspective and cause points that are farther away to be closer together. And then what I want to do is take this vector from the camera to the point and project it onto my camera's U vector, and that will give me a U point. I project this vector onto my camera's V vector, that gives me a V point. And then say this point, this distance where my W ray intersects this plane, I'll call that D for distance. I divide U and V by distance, and there's basically my 2D point. And there are a lot of other problems to solve that are a lot more difficult. Like if a polygon falls, if it is clipped by my camera edge, then I have to cut up that polygon, and I have to cut it up into pieces before I can render. And then aside from adding in controls, there are a lot of small things to get working, but as far as this problem of projecting a 3D point onto a 2D plane, it's really pretty easy. It's basically just a projection. So that's my video on vectors. Hope you enjoyed it, and thanks for watching.